Okay, welcome to the next problem from section 2 of the IIT JEE exam 2023 part 1. Okay, and so this is a problem, also actually pretty standard problem of how to handle capacitance in parallel plates when only partially it's filled with one dielectric and another part is either air, which is a dielectric of dielectric constant 1. Okay, so what will be the next what is the capacitance of the container at some point? Okay, so the container being filled with a liquid or dielectric at constant 3 at uniform of this, so they give you volume rate. From the volume rate you gotta figure out what's the rate of filling in terms of this dimension along this dimension, and then you know how high that is, so you will know how far it has been filled. Okay, and there are 4 choices and only one of them is right, and actually this is going to be an easy problem to solve. So let's see. I can just solve it in this margin here, but I want to explain to you how the problem goes in general. Okay, so if you have if you have a dielectric if first to know that if a parallel plate capacitor and the whole thing is filled, so this area is A and the separation between them is D, and between them is dielectric constant epsilon. Okay, so permittivity is equal to say dielectric constant epsilon r. Epsilon is epsilon naught epsilon r. So these are like this dielectric constant, and this is the permittivity of free space, and this is the dielectric constant that gives you the permittivity that's in there. So if this was just vacuum, it will be just epsilon naught. So the capacitance of this thing will be epsilon, how big the plates are, divided by how separate they are. So the closer they are, the more the dielectric constant. Another thing to notice is if I have a one plate and I have another plate and join them in parallel. Okay, so if this has a dielectric constant C1 and C2, then this will be equal to having dielectric constant C will be C1 plus C2. And the third trick that we will need is if I have so these are the leads that go into the 2 plates. Now if I were to fill up to that point, with one dielectric constant, so this one will say permittivity is epsilon r, then we would have and this side is say epsilon. Let's talk about this epsilon itself. Okay, so let's say some 2, and this side is epsilon 1, and this was height h1 and this one was height h2, but this side was let me say width of the plate, and this separation is d. So this will be equal to as if I had two plates so this with height h2 but filled with epsilon 2 with w and this distance d. This in parallel with this okay, so this with epsilon I have things mixed up, the epsilon 1 and this epsilon 2 and h1. Okay, so this is still w, this is w and epsilon 2, and this is still distance d. So these are parallel. So the capacitance of this will be equal to capacitance of this and this one. This will be C1 plus C2 1, and this is C2. I'm keep mixing. This is all 2's and this is 1 and this is 1. I keep mixing 1 and 2 here. So each one of them, but the dimensions are different. So if you look at this, at this point C2 will be using this formula epsilon 2, the area will be w times this height and the distance between them is d, and C1 will simply epsilon 1 same width h1 and distance same. So the C will be, you can say w over d is same epsilon 1 h1 plus epsilon 2 h2. So that's the answer, right? So in our case is thinking about this problem here, we need to figure out how high this is if the container is being filled with a liquid dielectric at a rate of 250 meter per second. This volume rate is given. So if the volume rate is given, then let's look at this bottom of this. So volume rate is very easy to use, right? So I have a container. Consider the bottom part is a container. The whole thing is, of course, this container. So say dH in time dt equals to dH. So and this side is d. Let's delta H, delta t, and this is this dimension, which is the w. So it has filled delta volume in delta t is d times w delta h, d times w times delta h. So if I divide by delta t, that's what is given by delta t. So that tells you what the rate of delta h is. So delta h will be just delta volume over delta t, the rate over dw, the separation, d is the separation and w is the width, so times delta t. So it's saying in 10 seconds and it's giving a rate 250, and it's also telling me so this is the width and separation. So keeping everything in centimeter, this is centimeter, so so delta H is simply going to be 250 centimeter cube over second. D is 5 centimeter and W is 50 centimeter, and time it wants is 10 seconds. 10 seconds. So this second cancels out and all of this cancel out, give me just centimeters unit, which we want, and this is 250, right? So this 250 cancels 250, so it's going to be 10 centimeter. So we got so in our calculation here, H1 is 10 centimeter and H2, so H2 is going to be 50 centimeter minus 10 centimeter, so 40 centimeter. Let's look at what other things are given. Permittive free space is given this, and saying the dielectric constant is 3. So what's given is this epsilon r is 3. Okay, so what's given, the epsilon 1 is 3 epsilon naught. So so and epsilon 2 is simply epsilon naught. So using this formula I got, C is just going to be, W was 50 in terms of centimeter, and and epsilon naught and epsilon naught will be common, times epsilon naught, and D will be 5 centimeter. So this centimeter cancels out, I don't need to convert this, and then you have a H1, epsilon 1 with H1, so 3 times H1 is 10 centimeter, plus 1 times 40 centimeters. So they have a 30 plus 40, the whole thing is 70 centimeters, and this is 10. So 10 times epsilon naught times 70, but this is centimeter, so I need to convert into 10 to the minus 2 meter. Now epsilon naught is also given, although a lot of people should memorize what epsilon naught is. So epsilon naught is given is 9 times 10 to the minus 2, and this is all SI units. So 9 times 10 to the minus 12. So this will be 9 times 10 to the minus 12. And then in that case it will be farad. And all of these are picofarad. Answers in picofarad. So pico, you got to remember, picofarad is 10 to the minus, if you don't remember what that will be, you can say milli, then micro, then nano, then pico, all factors of 1000. So this then minus 3, minus 6, minus 9, so it's going to be minus 12 farad. So we can just get rid of this, call it picofarad, and 101020. So I get 63 picofarad as an answer. So let's check out, and that's a B over here, exactly given that. So that's the answer is B. Okay, so there are, if you review what this problem is actually there's a little bit of fluid flow problem. So this part is a fluid flow problem, and this is going to stump people because this is the volume rate and you have to think about how it's rising. Okay, over here is how to break it up, a problem like this, into two parallel capacitor problems. And if you have parallel capacitors, then capacitance is add, not like resistor, right? In the resistor, you have a parallel resistor, they don't add like this. The inverse is add. All right. So you have to be kind of knowing those things, and the rest of them is really kind of trivial, but it does test something from basic physics. So this kind of thing probably was covered to you, covered in a introductory physics course, and it should be accessible to just a student who has taken a regular physics course. All right, I'm going to next video I'm going to do the third problem. Let me see where the third problem is. Did question 4, 5, and then here are 6 and 7 coming up. So this one is a ideal gas, some thermodynamics problem. And this one is looks like a gravity problem. When I do it, I'll come to that problem, some kind of gravity mechanics problem. All right, so I'm next going to do question 6. All right, see you in the next video. Bye.